Let's look at the results of our experiment, paper chromatography of marker pigments. What we did in the experiment was we took several different colors of water-soluble overhead projector markers and we put them on a piece of paper, just a little dot, and then we put the piece of paper in a cup of water and we let the water soak its way up the paper. And as the water soaks its way up the paper, it picks up and carries the different parts of the mixture that makes up the colored dyes in each one of the markers. So what I asked you to do was to record your results by looking at the colors in the paper and drawing them on your copy of the assignment as your data. And this is kind of what it looks like in some of the papers that I saw. This is like a visual average. So think about what was going on in the experiment. When we put the piece of paper in the water and the water starts to soak its way up through the paper, it picks up the mixture of the different colored dyes. And depending on how well each one of the parts of the mixture mixes with water, that's going to determine how far up the piece of paper the molecule goes. And then you can see its color. As each of the molecules moves a different distance, it separates each of the different colored dyes. Now, some of the molecules move farther than others because they're more like water and they can stay mixed with the water better. Using our rule of thumb, like dissolves like, molecules that are more alike in their polarity or in their attractive forces are able to stay mixed together longer and are carried up the paper farther. Some of the molecules are not as much like water in their polarity, so they don't go as far because they're not picked up and carried as much as the others. So what we can look at is how far did each of the different colored dyes go, and then we can use that information to rank them by their polarity by comparing to how far they went compared to water. If we know that water is a polar molecule, then we can use the rule of thumb that like dissolves like. Molecules that are more like water are more polar and therefore will move farther in the paper, and molecules that are less like water and are therefore less polar won't move as far. So looking at the distance that each one of these went, I'm just going to use the pencils here to represent the 6 different colored dyes. The water line and the blue dye moved the same distance in the paper, so we'll put that one up top. And then there was a black color that moved not quite as far as the blue color. The next distance traveled was by the purple colored dye, and then the next one was a red colored dye. There was a pink dye found in a couple of the markers, and then there was a yellow dye. So these are the 6 different colors and how far they traveled in the paper. Now, based on how far they go, we can rank them according to their polarities. Molecules that are more like water are more polar because water is a polar molecule. We can rank, for example, the blue molecule the most polar, the most like water. So I'm just going to draw that one right here. The blue colored dye is the most polar. The one that's the least like water, the one that didn't go as far as the others, was yellow. So I'm going to rank that one the least polar, the least like water. And then I'll continue down the line. The black was less polar than water, but more polar than the yellow one. The purple was the next one, and then the red one, and then the pink one. So these are the orders in which the molecules are arranged according to their polarity. I didn't space them evenly, but in terms of their relative polarity, we can say that the blue is the most polar because it's most like water, and then rank the other ones according to how far they went compared to the water. That's the idea behind chromatography. Now, there's another question that asks about other kinds of markers. The markers that we've been using in class might be permanent markers, or they might be water-soluble markers. Where did my permanent marker go? Here we go. Sharpies are examples of permanent markers, and then the overhead projector markers, water-soluble. Now, inside the markers is a liquid in which the different dyes are mixed, and then as you write on paper or something, that liquid carries the dye out, and then the liquid evaporates away from the paper or whatever you've written on, leaving the dye behind. Water-soluble markers and permanent markers have a different liquid that's in them. It might either be xylene or ethylene glycol. These are 2 common solvents used to dissolve the inks in markers. And the question is, which one of these two would you expect to find in a marker that's permanent, and which would you expect to find in a marker that's water soluble? And how would you tell? By looking at the structures of the molecules. Well, when I look at the molecules here, I'm looking for evidence of how they would attract to water. Water looks like this when we draw its structure. And it has two pairs of unbonded electrons, which I also see over here on ethylene glycol, on those oxygens. One thing we know about water is that it can make hydrogen bond attraction to other molecules because it has one of those three elements that we look for: fluorine, oxygen, nitrogen. Hold the phone. That's how you know how to look for hydrogen bonding. And if there's hydrogen attached to any of those elements, that also is part of the hydrogen bonding attraction. Hydrogen has a lower electronegativity than oxygen, so electrons are pulled more towards the oxygen side of the bond. And also the unbonded electron pairs there give oxygen a strong negative charge on that side of the molecule, hydrogen a strong positive charge. If we see that same thing in another molecule, that strong positive and negative in oxygen and hydrogen, then that's an opportunity for opposite charge attraction by hydrogen bonding. Over here in the xylene, there's no oxygen, fluorine, or nitrogen. Although there are slight differences in charge, making each of these hydrogens slightly positive and the carbons slightly negative, it's not as large a charge difference as is needed to attract water more towards xylene than more towards other water molecules. The other rule of thumb: molecules stick to their own kind. Molecules that are more alike in their polarity or attractive forces will be able to mix. Water could attract to ethylene glycol like this. I could draw a water molecule like this here, with the opposite charges of the oxygen attracting to the hydrogen in the ethylene glycol. Let me draw a few little dots right there to represent the hydrogen bond attraction. So that's one way that water could attract to ethylene glycol. The oxygen in water could attract to the hydrogen here in the ethylene glycol. Not so much over here. These hydrogens don't have a strong enough positive charge to encourage water to attract to xylene as much as it would attract to other water molecules. We could also have an attraction with the oxygen. If I had a water molecule floating around in this orientation like that, the positive charge in the hydrogen and the negative charge in the oxygen could attract like that. So there are opportunities for hydrogen bonding on each end of the ethylene glycol molecule. So that's the one that you would expect to find in a water-soluble marker like this. The xylene you would expect to find in a permanent marker. Permanent markers can't be washed away with water because water doesn't attract to xylene very well, and anything that would mix with xylene, like the dyes that are in the permanent marker, would likewise probably not be very attracted to water because they're more attracted to xylene and wouldn't wash out as well, making them permanent. Water soluble, attraction to hydrogen bonding in water. Not water soluble, not an opportunity for hydrogen bonding with water. So as you're working your way through answering the questions, please make sure to keep in mind those rules of thumb: like dissolves like, and molecules stick to their own kind.